Hey, what's up, guys? This is Chung here again. So today, let's take a look at today's daily challenge, which is number 173, binary search tree iterator. So, so the problem says implement a binary search tree iterator that represents an iterator over the in-order traverse, right? So in-order traverse means the left, middle, and right? That's the in-order traverse. And you need to initialize the tree, and then you need to call implement to method, which is the first one is the next, second one is the has next, right? So which means that next gives you the next one. So in this case, let's say we have a 1, 2, and 3, right? So the first next will give you 1, and then if you call next again, it'll give you 2, and then 3, so on and so forth. Has next just tells you that if you have any unvisited uh, node in this tree. Right, pretty straightforward. And then it gives you some examples here, right? So here's example one here, and basically for the in-order traverse, you got this one, 3, 7, and then what? And then 9, right? 9, 15, and 20. So that's the order of traverse. Okay, cool. And so actually for this problem, the easiest way will be like we just do a when we do the init, right? We just do a in-order traverse, and then we store everything. We store all the nodes into a into a queue, right? And then whenever we have a next, we just do a queue pop left, right? So which means that we have this 7, 3. So we do a pre-process. We have 7, 3, 9, 15, 20, right? In this queue here, and every time we just pop. When we do the next, we pop this one out, and that will be our final answer, right? And the has next just simply to check if this queue is empty, right? So that's the first approach. I mean, I guess everyone can come up with that approach, right? I mean, but today I want to maybe focus on this follow-up question, right? So still, we want to implement this next and has next to run in average O1 time and use OH memory, as you guys can see here. So for our first approach, the the space complexity will be O of n, right? Where n is the total number of nodes. But here's the follow-up. We want to have like a O of h of memory, and next and has next to run average O1. So average O1, see, so it's not strictly O1, right? I mean, basic, it's an average O1, and this is the OH, O of H. So so to be able to solve that, every time when you get, I mean, it already gives us a hint, right? Basically, H is the height of the tree. So which means that we have to somehow stores the what some indicator on each level because H is the level of the tree, right? For example, if we have this tree, I'll simply write some trees here, probably I'll just write three levels here, maybe this one. Okay, how about that? Yeah, I think this is good enough, right? So since it only wants us to use an average of OH memory, so which means that we have to somehow store the indicator of each level, right? And since this is a binary search tree, it's kind of makes obvious that we just need to store, I mean, the leftmost node on each level. So which means we have this one stored in the stack here, right? So we have this one, this one, this one, and this one. So at the beginning, we have four nodes stored in the stack. Okay, and every time when we are trying to get the next calling the next nodes here, we simply do a pop, right? So we pop the current smallest. Basically, we pop the ones on the top, which will be the smallest number and which will be our next number, right? But after popping that, we have to somehow uh, put more nodes into it so that we can do the next pop. since as you guys can see here, we are only storing the leftmost nodes here, right? And see, so when we do the next first, so this node will be popped, right? And now, and this, I think this is good, right? Because this node doesn't have anything, right? This is like the first one is the leaf node, right? And now we have this one. Now the stack only has three nodes, which is this one, and this one. And the next time when we pop the next, right? Since this next this node has a right subtree, right? So which means that we cannot simply uh, pop this thing out. We have to add the nodes into the right subtree. Basically, every time we do a pop, right? We check if the current node has a right subtree. If it has, then it means that okay, before returning the result for the next, we have to basically do the same thing for the right subtree, right? So we start from here and then we add the leftmost nodes to our stack for the right subtree, so that later on, this one will be our next thing to pop, right? So on and so forth. And same thing for the has next is pretty straightforward. We simply check if the stack is empty, right? So as you guys can see here, so it's basically every time after popping a node here, if we have a right subtree, right, we just do the same thing as if we were doing this like init for the entire BS tree, the binary search tree, right? We also traverse to the end of this tree. Let's say we have like another one here, right? So and then here we'll add, right? We'll add this one, this one, this one, this one. We'll append to the stack, and the next time this node, I mean this node will be popped out, right? And then this node, and this node, and then when we're popping out this node, we see okay, we have another like right subtree, right? And then we'll add this one to the stack, add this one to the stack. We keep doing it until we have traversed to the entire tree, right? And then as you guys can see, and that's why we call this next method, an average of all one, because after popping these things here out, right? I mean, we have to traverse to the to the right subtree, right? And we have to do a O of h a another O of h, right? Another O of h traverse to get all the leftmost nodes for the right subtree. So why I call this an average of O1? Because of course you can argue that if we have like a very extreme case, right? I mean there's like the right subtree, it's like this, right? But that's gonna be the worst case scenario, right? I mean the best case scenario is like a balanced tree, right? So whenever it's a balanced tree, we have this one, right? If it's a balanced tree, right? So I mean, at most we will, if it's a balanced tree like this, right? So whenever we are at this node here, right, we'll get uh, another O of h, but this O of h will be like a pretty small number here. I think that's, to me, I think it's kind of similar, close to average of O1. I think that should be okay to consider as an average O1. Yeah, for this part, I'm not 100% sure, but this is as close as I can get. I mean, all right, so let's start the implementation, right? So I think the implementation is pretty short. It's not that long. We have a stack, right? And then we add the leftmost node for on each of the level. So we just do a simple while loop here, right? Starting from current root, what current is not empty, right? And then we just do a self dot stack and append the current, right? And then we just assign the current to the left, right? So we keep basically we keep going to the left and then until we have reached the end. And so the next is simply return if the self.stack length is greater than 0, right? And so for the next part, right? So next part we have the answer, which is the self.stack dot -1, right? And then value. So that will be our answer, right? Because the top one is always the our next numbers, right? So and then we simply return the answer, and then before we return the answer here, we we do a check, right? If this uh current, we pop the current one first, stack dot pop, right? So we pop this one and then we check if the current one has a right subtree, right? And then we do the same thing for the subtree, which means that we assign the current to the current dot right, right? And then we do another while loop here, while current, and then we do a self dot stack dot append current, and then we do a current equals to the current dot left, right? So basically we are adding the left subtree, the leftmost nodes for the right subtree. Mm, yeah, and if I run the code here, that'll accept it. And then if I run it again, yeah. So for this part, I mean, since we have already, I mean, the best case for this one, I mean, the best case for this one will be a O of 1, right? Because if there's no right subtree, right, and then the so this next will be O1, and the worst case scenario is the is of H, O of H of the right subtree. But we are considering this the binary search tree like in the either the in the average case, so maybe O of 1. Yeah, let me know what you guys think about this approach. If it can be considered as a O1, I think it should be okay because I couldn't find any other solutions. But yeah, cool. I think that's pretty much I want to talk about for today's daily challenge problem. And yeah, thank you so much for watching this video, guys. Stay tuned. See you guys soon. Bye bye.